mole refers to Avogadro's number. So 1 mole is equal to 6.02 times 10 to the 23rd particles of anything. So just like 1 dozen equals 12 donuts or bagels, 1 mole is going to represent this huge number of particles. So 1 mole of silver refers to 6.02 times 10 to the 23rd atoms of silver. 1 mole of carbon dioxide refers to 6.02 times 10 to the 23rd molecules of carbon dioxide. So again, 1 mole is a unit. We're representing a huge amount of atoms. But right now we're just going to focus on the moles, and we'll get into tomorrow with the 6.02 times 10 to the 23rd. So the mole ratio is a whole number ratio between components of a balanced chemical reaction. So the coefficients in front of each species lets you know how the reactants and products are proportional in terms of their number of moles. So for example, when we manufacture ammonia, we have this simple synthesis reaction. If we look at the coefficients, this means that if nitrogen and hydrogen are reacted in a 1 to 3 mole ratio, nitrogen has a 1 out in front here, and then hydrogen has a 3 out in front, so that's where the 1 to 3 comes from. You will produce 2 moles of ammonia. Now, this is important because equations are just like recipes. I can double it, I can triple it, I can cut it in half. So if a problem calls for 10 moles of ammonia, you can use that 1 to 3 yields 2 proportion in order to determine how many moles of nitrogen and hydrogen you would have to have in order to react and make that 10 moles of ammonia. So let me just bring this pen up. For this, if you scale the ratio up by a factor of 5, so when I went from 2 to 10, I multiplied it by 5, so I'm scaling it up by 5. Whatever I do to one coefficient, I have to do that to all the other ones. So here I had a 1 to start, and if I multiply that by 5, that means I would have to have 5 moles of nitrogen. And then again with the 3, I'm going to do the same thing. I'm going to have to multiply it by 5. Again, whatever I do to one coefficient, I have to do to all of them, which gets me 15 moles of hydrogen. Okay, so that 5 to 15 yields 10, still maintains that original 1 to 3 yields 2 ratio that the original coefficients gave us. Now, we can use dimensional analysis to determine the number of moles of reactants and products. We did this for our unit conversions. We did this earlier in the unit when we talked about converting between moles and mass. So we're going to start with the moles of our given. Remember, we put whatever the given unit is in the bottom, and then whatever we're trying to get to, we put in the top. Except what we're going to be looking at are the different formulas. All right, so here we're going to first balance the equation. So we need a 2 in front of the HBr, and then we have 1s in front of all the other compounds. So now we want to say that if we have 3 moles of hydrogen bromide that react, how many moles of hydrogen gas will be produced? And this is with the assumption that magnesium is in excess. We have plenty to react with the hydrogen bromide. So you're going to start with what you are given, which is 3 moles of hydrogen bromide, and this is where you do need to write the chemical formula. We talked a little bit earlier about how you didn't necessarily have to show it, but with this mole to mole conversion, we need to show it. So we have 3 moles of HBr. So here on the bottom, I'm going to still have moles of HBr. Okay, again, the units have to match. I have a 2 out in front of the HBr, so I'm going to place the 2 with that unit of moles of HBr. And we're trying to find hydrogen gas. And up here we have hydrogen gas. So we have 1 mole of hydrogen gas. So we would cross out our moles of HBr, so I'm left with moles of hydrogen, and then 3 divided by 2 gives me 1.5. So I have a total of 1.5 moles of hydrogen gas will be produced if I start with 3 moles of hydrogen bromide. All right, doing another example, and we balance this chemical reaction. We put a 3 in front of the zinc acetate. We then needed 2 in front of our sodium phosphate. Oop, these kind of got off center. 6 and a 1. So here, they're all straightened out. So we have 3, 2, 6, 1. So that's our ratio. 3 to 2 for our reactants will make 6 to 1 of our products. So just like before, we're going to start now with what we are given. So 2 moles of our sodium acetate. Okay. Okay, now because I'm starting with moles of sodium acetate, I need to then put in the denominator the same unit of moles of acetate. I find that in my chemical formula. Okay, I have a 6 out in front, so I'm going to carry that 6 down here. So I have 6 moles of sodium acetate. Okay, and then I want to go to sodium phosphate. So how many moles of sodium phosphate do I originally need to start with in order to produce that 2 moles? So I'm going to then place the 2 here for my sodium phosphate. So 2 moles of sodium phosphate. Okay, I can cross out my moles of sodium acetate, so I'm left with moles of my sodium phosphate. Okay, and then 2 times 2 divided by 4 gives us 0.67 moles of sodium phosphate. Okay, so again, we started with what we were given. We put the same unit in the denominator along with its coefficient, and then our target number of moles of sodium phosphate, we place that unit up above with its coefficient of 2. So again, everything's coming from this balanced equation, multiplying across the top, dividing by the bottom, and then that is it. All right, so we're going to practice these a bunch tomorrow in class, so just come with your notes all set.